Hello, everybody. It's great to see so many connected for this webinar on magnetic reconnection in plasmas. My name is Jonathan Graves, and you'll be pleased to hear that I'll only hold things up for a few minutes. I'm just here, in fact, as Editor-in-Chief of Plasma Physics and Controlled Fusion to welcome you to this webinar. This is the first of a series of webinars that we're planning. The next one to be held, which will likely be in June or July, will be on the important topic of negative triangularity plasma configurations and tokamaks. But today, part of the motivation for PPCF in hosting this first webinar on the topic of magnetic reconnection is to present the journal as a welcome home for all the communities working on plasma physics. Magali Miraglia from the Aix-Marseille University will introduce speakers in the fields of natural plasmas and laboratory plasmas. And we hope that by bringing together these areas under the common theme of reconnection, that we might all learn something new, and also ideally, there'll be cross-fertilization from one topic to the next. So without further delay, I'll welcome you in the capable hands of Magali Miraglia, who's the chair of this webinar. Thank you.
So thank you, John. So hello, everyone. So I'm Magali Miraglia. I think you should now see my screen. I hope so. So welcome to the webinar, so dedicated to magnetic reconnection in space plasma and fusion plasma. And in particular, today we want to highlight challenges at large and small scales. So indeed, in fusion and space plasma, as you know, magnetic reconnection is an important field. And it's why we want to do this webinar to bring together these two communities, and in particular, the speakers today will try to highlight common issues that they both face. So the webinar program is the following. So first, we will have a tutorial talk to give you the keywords in both space and fusion plasma. And then we will have short presentation, half on dedicated to space plasma and half dedicated to fusion plasma. At the end, we will have a general panel discussion. And so during the talk, you will have access to the chat box. And so you are really free to ask all your questions in the chat box, in particular, students and young researchers. So please feel free to ask questions. And so we will keep an eye on the questions. And we will go back at the end of each presentation on one or two basic questions you had during the talk, and I will keep the further question for the panel discussion at the end. And so we can start. So first we will start with Daniela Grasso from CNR in Italy on the tutorial talk, so dedicated to a magnetic reconnection.
Thank you, Magali, for the introduction, and thanks. Can you see my screen, by the way?
Yes, Daniela, we see your screen.
Sorry. And thank you to all the colleagues listed here. So let's start with defining magnetic reconnection. The slide is not working. Okay, it's a process. Magnetic reconnection is a process which takes place in conductive fluid and plasmas. It consists in a topological variation of the magnetic field. And so you see here you have two magnetic field lines which are distinct at the beginning, the red and the blue line, which at a certain time they tear and reconnect, changing the topology of the magnetic field with mixing the colors of the two magnetic field lines. And it is generally accompanied by a fast release of magnetic energy into heat and order kinetic energy. It's a local process which causes global changes. Here we have, in this picture, we have a magnetic field which opposite direction with a neutral line. At a certain time, a magnetic reconnection process occurs, and you see the topology of the magnetic field changes completely, giving rise to a magnetic island in the magnetic field. And the point where the magnetic field line cross and tear and reconnect is called the X point. Typically, this process is accompanied by a formation of intense current density layer, like the one shown in this simulation of magnetic reconnection process. So where does magnetic reconnection occur? Well, for instance, on the sun's surface, where tremendous explosions known as solar flares occur. In a few minutes, they heat material up to many millions of degrees and release a huge amount of energy. Here is a sketch of what happens in this sketch here, and you see when you have magnetic field lines which are highly stretched, it may occur that magnetic field lines with opposite direction come very close and they can tear, reconnect, and you see here you have an X point. In the magnetosphere, well, magnetic reconnection occurs at the day side of the magnetopause when the interplanetary magnetic field encounters the Earth one, or at the night side in the magnetotail. NASA and ESA missions like MMS and clusters have been specifically designed to detect magnetic reconnection. So, also many laboratory experiments have been projected and conducted to explain the measurement of these missions in the space. In the labs, well, for instance, magnetic reconnection occurs in thermonuclear experiments. In tokamak device, magnetic reconnection is something that you would like to avoid. Here is an example in this picture here on the top, an example of how magnetic reconnection appear as island chains in a cross-section of the toroidal device. This is in some way a two-dimensional view of the problem, but when this island grows and overlap, the third dimension can be no longer ignored, and there is a generation of magnetic chaos, like here in the red region, okay? Magnetic chaos is the fingerprint of reversed field pinch devices. Here, for instance, is the result of a numerical simulation where you can see the reminders of a chain of 8 islands that were present at the beginning of the simulation. Also in stellarators, magnetic islands have been detected. Here you see a chain of 6 islands, okay? Then there are the dedicated experiments about which Tao Ji will talk, VTF, MRX, TRX, flare, and many others. So now, let me give you a bit of a theoretical framework for understanding the definition given before. First of all, why it is so amazing that the field line reconnect? Well, the answer is because usually they cannot. If you consider an ideal plasma governed by the ideal sum law, so this E plus 1 over C B equals B is equal to 0, and which is actually a very good approximation under several circumstances. So if you take the curl of this expression and then use the Faraday's law, you get an equation of evolution for the magnetic field. If you integrate this equation over a surface S which is moving with the fluid, you get this expression here. The first term is the rate of change of the flux defined here through the fixed surface S, while the second term represents the increment of flux, which is swept out per unit time by the contour moving with the local fluid velocity. So the point is that this expression tells you that the magnetic flux is conserved, okay? So the magnetic flux is frozen into the fluid, and this is what is called the frozening law. Two plasma elements which are connected at a given time must remain connected at later time. Then, as I said before, intense current layer forms. Why? Let's think to a simple example. You have a magnetic field which is in the 2D plane, which is directed along Y, and which has a neutral line in the middle. Related to this magnetic field is a current density. Okay, you can estimate that this current density, which is directed in the out of plane direction, from dimensional analysis as B, the intensity of the magnetic field divided the variation scale of the magnetic field. So if you now push towards each other the magnetic field lines, this L distance will go to 0. And so the current density will go to infinity. And so will the J cross B force, which tend to opposite the getting closer of the magnetic field lines. So what happens if some effect limit this strong current density? Okay, so let's suppose that there is some non-ideal term in the Ohm law. Okay, so is E plus 1C over B cross B is not equal to 0. The magnetic field line equation changes. The magnetic flux is no longer conserved. And so the magnetic field lines are not can tear and reconnect now. So let's suppose the simplest thing we can think of is so that resistivity is the breaking mechanism for the frozen-in condition. You get an equation of the evolution of the magnetic field, and you have here a diffusion equation. So if you balance this term with the diffusion with the first term, you get a resistive time for reconnection to occur. But this is a long time because it is related to a macroscopic scale. So the essence, the essential thing of reconnection is local scale, as I said before. So let me normalize this equation with the typical propagation time of phenomena in MHD, which is the Alpen time. If you do that, you get this equation where you have a parameter related to the so-called Lundquist number, S, which is equal to the ratio of the resistive time over the Alpen time. This number is very huge. It's 10 to the 7 for a tokamak, for instance, and 10 to the 12 for solar corona. So this number is really small. So when this term can become important? Well, in a region where the magnetic field or the velocity field go to 0. So this is what is called on a local, this happens on local scale, and this is what defines the diffusion region where magnetic reconnection can proceed and in a faster way compared to the resistive time written here. The first theory that has been developed to explain this phenomenon relied on resistivity as the breaking mechanism for a frozen-in condition. So we now see two models up to describe driven and spontaneous magnetic reconnection in the frame of MHD theory. The Sweet-Parker model is resistive, MHD, two-dimensional, uncompressible, and stationary. Okay, so magnetic field lines are pushed toward each other by a velocity field. The magnetic field lines here are directed along Y, and the velocity field along X. The the Sweet-Parker time, I don't have the time, of course, to give the calculation, but the Sweet-Parker time is equal to the square root of the resistive times the Alpen times. So let's look at the numbers. For solar flares, the prediction, according to the Sweet-Parker theory, would be of 2 months, to be compared with the observed time of 15 minutes, 1 hour. For fusion plasma, for instance, a sawtooth crash related to a reconnection event would occur on a 3 millisecond scale length, while it is the observed one is 100 microseconds. So we have a problem. So the question we might wonder is the resistivity the right mechanism? So keep the question for later on. Here is a model which has been adopted in the framework of tokamak fusion, or thermonuclear fusion, and is a model which describes the spontaneous magnetic reconnection process in a tokamak. It's a 2D model, incompressible and reduced, so it assumes a strong guide field. And here the magnetic field is given by a constant field in the z direction plus a magnetic field in the perpendicular plane. The velocity is expressed in terms of the string function and the magnetic field on the flux function. So the equation you written here comes from the Ohm's law and from the plasma motion equation. And this problem can be solved linearly by standard asymptotic matching technique. So you identify an external region where the ideal MHD holds and where you can neglect the resistive terms, and an inner region where you have to retain this term. The most important linear result of this problem is the determination of a threshold for the instability to occur spontaneously. So there is a parameter delta prime, which is the logarithmic derivative of the outer solution, which tells you that if delta prime is greater than 0, magnetic reconnection can occur spontaneously. So including the resistivity in the Ohm's law is the first and simpler thing to do, but theories based on this effect do not work too well for the low resistivity, due to the low values of the resistivity. So it might be the resistivity is not is the starting mechanism, and then other effects come into play and give a boost to the reconnection rate. Or it can be that other effect can break the frozen-in condition. Here, in the frame of a two-fluid model, I have taken into account, for instance, the resistivity effect and the electron inertia that can break the frozen-in condition, while the Hall effect and thermal effect can give a boost and increase the growth rate. So there are many scale lengths which enter into play in this problem. So answering this question and solving this problem requires to look at the magnetic reconnection from a different multi-scale and multi-physics approach to connect what happens at a microscopic level to the large scales. And the problem is made even more tough by the wide variety of plasmas and different conditions in which magnetic reconnection occurs. It occurs at a large scale, and it occurs at large scale, and it occurs in a system, for instance, gamma ray flares, where you cannot neglect the relativistic effect. So one of the problems is which is the right description, how to take into account where use MHD, where use kinetic description, and how to incorporate the relativistic effect. Also, the geometry is an important issue, because when you have a strong guide field, a 2D description can be adopted, but not always double periodic condition, which fits, for instance, the tokamak geometry, can be adopted, for instance, in space plasmas. So the problem of which description to use, 2D versus 3D, and the boundary condition is another issue which is important to be take into account. The mutual influence of between magnetic reconnection and turbulence, because often it appears that magnetic reconnection occurs in turbulent background. In turbulent background. Okay. And then spontaneous or driven reconnection. Driven model for magnetic reconnection are good to study the problem, but most of the time magnetic reconnection occurs spontaneously. So these two perspectives must be integrated in such a way to understand how the necessary conditions for the reconnection process to occur spontaneously are self-consistently created in the plasma. Finally, the role of the numerical simulation, something like the ghost in the room, because of course, all these nonlinear physics can be addressed by numerical simulation. And so the many possible descriptions have to be compared. I want to close, I'm going to, oops, sorry, to close. Trying to give you, how can I say, the flavor or where we are now, and of some recent theory. Kinetic reconnection is believed to be fast, but many astrophysical plasmas fall in the MHD range. The plasmoid theory tells you, which is a recent theory, actually predicts that when a sweet particle carrying sheet becomes so thin and elongated, it may disrupt in a plasmoid chain, increasing the growth rate of the reconnection process. Okay, so here is an example of plasmoid formation in resistive plasma, and here in a collisionless turbulent plasmas. This carrying sheet instability, and I'm finishing, have been utilized at PPPL to design a new plasma transfer exploiting the kinetic energy generating during magnetic reconnection. So thank you for the attention.
Thank you, Daniela. So before going to the talk of Giulia, maybe one basic question for Daniela. Can you precise, so you said that you have magnetic reconnection in laboratory plasma, in space plasma. Can you precise the magnetic reconnection nature difference in space and space plasma?
In space, sorry.
In space and fusion plasma, sorry, it's me.
Sorry. Okay. Well, I would say that the first thing that comes to my mind are the scale on which reconnection can occur in space plasmas, because even though there are small scales, there are nanoflares and this kind of phenomena. The most are, of course, on large scale. And in plasmas where an MHD description is suitable. While in fusion plasmas, I would say that an MHD description is not enough, and we have to go to more refined model to explain this phenomenon.
Thank you, Daniela. Thank you very much. So now we will go with Giulia Cozzani. So Giulia is from University of Helsinki, and she will speak on magnetic reconnection in a near-Earth space plasma.
Thank you, Magali. Okay. Do you see it now in presenter mode?
Yes, Giulia.
I hope so. Okay, thank you very much. Yeah. So, hi, Magali, also for the introduction. As you said, I will be talking about magnetic reconnection in near-Earth space plasmas, and the idea is also to provide you with a bit of the challenges of the open questions that we have now in this field. So, as Daniela already said, the reconnection, of course, occurs in an incredibly diverse collection of astrophysical settings. So these are some nice figures, let's say, to show you where it happens, but it is really a process that happens throughout the heliosphere and even beyond. For example, it is believed even to power the jets that we see at active galactic nuclei. But let's say if we now look at these different plasma in a little bit more maybe boring way, but more informative, we can put them in this kind of parameter space where we have an x-axis with the plasma beta, which is usually dominated by ion dynamics, and then on the y-axis we have the ratio of the electron plasma frequency and the electron gyro frequency, which is indicative of the electron dynamics. As you can see here, we have different words representing the different plasma. They are covering quite several orders of magnitude in these dimensional quantities. And here, this figure contains also some laboratory plasmas, for example, the MRX experiment that will be discussed by Antauji in the following of the webinar. But what is interesting about this figure is that if I overlay all the points of this parameter space, which are represented in the Earth magnetosphere conditions, you can see that a very sizable region of this graph is actually occupied by conditions that we might have at the Earth magnetosphere. And this tells us that the Earth magnetosphere is really an exceptional laboratory to study reconnection. Of course, we need to be careful if we want to extrapolate the knowledge at the Earth magnetosphere to these, let's say, distant plasmas, but still, the study of magnetic reconnection at the Earth can give us some information to study reconnection in other situations where we don't have the same data that we have at the Earth magnetosphere, as we will see. So indeed, reconnection occurs in the Earth magnetosphere in many of the regions associated with our planet. Daniela already presented this, but here I would just like to remind you that when we talk about near-Earth plasma, we are mostly talking about collisionless plasmas, so the resistivity is not the mechanism that is allowing magnetic reconnection to happen. Magnetic reconnection happens at relatively large current sheets like the magnetopause and the magnetotail current sheet, and this is extremely important for the overall dynamics of the Earth magnetosphere. However, there is now consensus of the fact that any time there is current sheets in the plasma, these will at some point reconnect. And so reconnection is a very important phenomena in the turbulent plasmas that we have in near Earth environment, such as the turbulent magnetosheet or the turbulent region close to the bow shock, in the bow shock transition regions. Now, as I was saying before, the Earth magnetosphere is the best laboratory at our disposal because we can go and investigate magnetic reconnection with in situ spacecraft measurements there. And here I just wanted to highlight the missions that have provided, let's say, the vast majority of the data to study magnetic reconnection. There has been other missions such as THEMIS and others, but I would say that the main contribution was given initially by the cluster mission that was launched by the European Space Agency, and it has been providing us with the data since the year 2000. This was the first mission that was composed by 4 different spacecraft, identically equipped with the same payload, that were focusing mostly on the large scale or even ion scales in the plasma. But then the MMS mission, Magnetospheric Multiscale Mission, was launched by NASA in 2015. And this was also a multi-spacecraft mission with 4 spacecraft, but was mostly focusing on the electron scales. The main goal of MMS was exactly to study magnetic reconnection at the electron scales. And here I wanted to write down this baseline science goal for MMS, which is understand the microphysics of magnetic reconnection by determining the kinetic processes occurring in the electron diffusion region that are responsible for collisionless magnetic reconnection, and especially how reconnection is initiated. So as you may remember from the talk by Daniela, the diffusion region is very important for reconnection. It is the region where the plasma is no longer obeying the law of the ideal MHD and where reconnection is actually enabled. When we go from, let's say, single fluid or MHD description to a multi-fluid or kinetic description, we see that the diffusion region is in itself a multi-scale region. There is a so-called ion diffusion region at the ion scale where only the ions are demagnetized, and then an embedded electron diffusion region at the electron scale, so very, very tiny and difficult to observe, where both ions and electrons are now not longer frozen into the magnetic field and reconnection is enabled. So the main, let's say, goal of MMS was really to address the question of what is happening in the electron diffusion region, how is reconnection enabled there. And MMS was definitely successful in that. the electron diffusion region has been observed. This is a plot from the first paper by Birch and Waters in 2016, showing the first observations of the electron diffusion region. And this is a plot that is very typical for in situ observation studies. So we have a stack plot with many sub-panels showing all the different quantities observed by the spacecraft in the form of the so-called time series. So this is the time where the electron diffusion region is observed is actually very, very short, because the region is very, very small at the electron scale, that at the magnetopause, as in this case, correspond to about 2 kilometers in space. And we see that there are many quantities such as the magnetic field density, the velocity of both ions and electrons, and then the current, the temperature, the electric field, all of them showing specific signatures that were used to identify the electron diffusion region. Let's say, there are several cases of electron diffusion region crossings that has been reported, and in several cases this has been defined as so-called laminar electron diffusion region. And it is called in this way because, as you can see from this slide, when people have been trying, let's say, to compare the observation to the peak simulations, very smooth, very laminar, they obtain a strikingly good agreement between the observation and, for example, 2D particle in cell. So definitely for this kind of study, it was required to have a fully kinetic description in terms of the model, but then there was a very good agreement between the two. This leads me also to this slide, which is very busy, I know, but the only message that I want to give you is that we have seen during now several years of research that it is extremely helpful and beneficial for the study of reconnection to have a synergy between in situ observations and numerical simulation. Definitely we have high resolution, high quality data, but also a wealth of code that can help us address the different problems at different scales. So in this sense, I wanted to put several, let's say, example of local simulation, in the sense that a single current sheet is modeled, or even global magnetospheric simulations that now exist even in 3D. And here we have different kind of codes that can be hybrid, fully kinetic for the local ones, and even a combination of MHD and peak, for example. But if we go back to our laminar electron diffusion region, what it turns out is that this is not the entire story. Indeed, there were some cases in which we observed a sort of patchy electron diffusion region, which is more complex. For example, the energy conversion is not positive throughout the region, but it has patches of negative and positive energy conversion. And of course, here this poses some question, and in particular, what is dictating the laminarity versus the patchiness of the electron diffusion region. There has been a relatively recent study from 2022 that basically gathered all the electron diffusion region events that has been observed with MMS, trying to address this question. And they came to the conclusion that the predominant source of the patchiness or the complexity in the electron diffusion region was due to the time variability of the inflow in magnetic field direction. So it's not surprising that are the conditions at the larger scale that are dictating the laminarity versus the patchiness, but yet this is still somewhat an open problem that require further studies. And one reason for that is that the MMS constellation is very, very close together at the electron scale. And while this allows us to study the electron diffusion region, let's say with multi-point to a very high level of details, on the other hand, doesn't allow also to know what is happening at the inflow or upstream region. And for that, cross-scale and multi-scale observations are needed in order to address this question. So this was just one of the challenges that we have. Now my idea was like to bring you very quickly actually through other challenges and open questions. Many of them are actually requiring a cross-scale approach. So one of these is the reconnection onset, especially in weakly driven current sheets. So as Daniela was mentioning, we want to know how reconnection is actually starting, when it can start kind of self-consistently and without being driven. Then also the interplay with the waves that can lead to 3D effects. The role of anomalous resistivity is also not very well known nowadays. The large-scale X-line topology is also something that is very difficult to know with a very small constellation of 4 points. So we need either more points or some other method combined with simulation to fully understand, for example, the extent of the reconnection line in the magneto tail. And then also the role of turbulence is something that has become increasingly popular, let's say, in the last years also, because there has been these observations of very turbulent reconnection, but is also contain many open questions. However, we are, let's say, quite lucky because there will be new opportunity to address these open questions in the futures, because there are multi-scale and cross-scale missions that are coming for us. So one is the Helioswarm mission that will be launched in 2029 by NASA. And then there is also Plasma Observatory, which is currently in competitive phase A at the European Space Agency. So with that, I'll just thank you for your attention, and I'm happy to take any questions.
Thank you, Julia, for your nice talk. Can you precise, so you speak about ion scales and electron scales, and can you precise, in fact, the rangings of these scales in the space plasma? Because I think it's very different from the one in the fusion plasma.
Yeah, that's a good point. So I can go back maybe to this, because of course, in the magnetosphere, like the conditions in terms of magnetic field density, temperature, they change quite drastically. So these scales, of course, can also vary if we take, if we think about the Larmor radius, or also the ion inertial length, electron inertial length, which are the most commonly used, for example, to have a sense of the scale of the diffusion region. They can vary a lot. As an example, at the magnetopause, the electron inertial length can be of the order of a few kilometers, let's say 2 kilometers, so that the ion scale would correspond to about 80. And in the magneto tail, we have a lower density, so usually the scales are a bit larger. We are talking about 10 to 20 kilometers for the electrons, and then a bit larger, of course, for the ions. So this puts a lot of constraint also on the kind of measurement that we might have, because at the magnetopause, 2 kilometers means that the spacecraft should be really, really close together in order to all observe at the same time, for example, the electron diffusion region. This is beyond, let's say, the technical possibilities. So, for example, the minimum interspacecraft separation that we had for MMS was about 6 kilometers. And this was already, let's say, something that was never achieved before.
Thank you, Julia. So just to remark that in fusion plasma, electron and ionic Larmor radius are much more smaller.
Yeah.
Thank you very much. So now we will go to the next speaker, who is Emanuele Poli from IPP in Germany, and he will present a talk on large-scale magnetic reconnection in tokamak.
So please tell me when you see these presentations, because at the moment I see myself, but not the slides.
Yes, we can see your presentation, Emanuele. You can go.
Okay, thank you very much. So welcome to the first presentation in this webinar, which is devoted to reconnection in tokamaks, and this is in particular about large-scale reconnection. Here, just a quick reminder: the tokamak field, magnetic field, is the superposition of two components. One is a strong toroidal component, which is here in green, and a weaker poloidal component, which is here in yellow. So this superposition of green and yellow leads to twisted magnetic field lines, which are depicted here in blue, as you see. We are in a situation of strong guide field. We have large Lundquist numbers and correspondingly very small Sweet-Parker reconnection layers that are much smaller than the typical, let's say, drift scale or non-MHD scale, which is the sound alarm radius, as was introduced by Daniel at the beginning. What is important for us here is that this twisting of the magnetic field lines is not the same everywhere in the tokamak. It changes with radius, and this can be described by a safety factor Q, which is basically the number of toroidal turns you have to take around the torus following the field line to get to the same poloidal position. Here you see an example for clarity. If you start here from the top, you go once around the torus, you land here at the bottom, and then after the second toroidal turn, you will be back at the same position. So in a tokamak, there are some surfaces on which the field lines close on themselves after a low number of toroidal revolutions. Here you see a few of them. Why these are important, we will see in a second. First, I would like just to remind you that we are in a situation where we have a strong guide field. So it's guide field reconnection. So if you magnify a given region of the plasma, it looks like this. Now this is really the theoretician's view of things. You can always align one axis of your reference frame with the magnetic field on a given surface. And so if you look at the projection of the field lines left and right to that surface, projection onto the XY plane, then the field lines look like this. This is the situation you expect for reconnection to take place. So the reconnecting field is perpendicular to and much smaller than the equilibrium field on a given surface. Why are these low order rational surfaces so important? Actually, we know the answer already from the first presentation. The fact is that tearing instability favors long wavelengths, and on these low order surfaces, you have space to accommodate very elongated structures, and those are more unstable. So I will just now go to two selected examples of reconnection in a tokamak, of large-scale reconnection. One is on the Q, when the Q equals 1 surface is present, and you have a kink instability driving the reconnection event. We will see in a second. And then we'll focus on more external surfaces where we can have spontaneous reconnection. And I apologize in advance for all the things I cannot say in this limited time. So, sawtooth reconnection, in this case, you have a hot plasma core that gets kink unstable, so it gets deformed as you see here. And this means that the central plasma is pushed towards the more external plasma, and this forces reconnection at these points. This you can see in this nice movie here. Black, so the white patch here is the hot plasma core. The plasma is rotating, that's why you see a rotation here. And at a given point, you see that this is smashing here against the outer surface, and the heat which was originally in the center is now redistributed on this more external surface. So this is an expulsion of heat and particles from the core, which limits the stored energy. On the other hand, it also helps flushing out the impurities from the core, and so it has also beneficial effects. It has also an effect I will mention in a second. And if this process goes on repeatedly, then you have the so-called sawtooth cycle, which is shown here. For this, you can imagine this is the central temperature, goes up, and then at the crash, there is this expulsion of the heat. Very interesting is that if you now measure the radiation from more energetic electrons, you see peaks at every crash event, which is the clear sign of reconnection taking place. This sudden currents so electron acceleration at the reconnection events. So this is not only a process which is very important for a tokamak reactor in itself. It poses some basic physics questions, which are very interesting in terms of the nature of the reconnection. This is again a case where the Sweet-Parker time is too long as compared to experimental observations. And indeed, if you go now to highly resolved simulations at realistic Lundquist numbers, you find this plasmoid instability that was already mentioned before. And this helps accelerating the reconnection rate a lot. So you see here the curve, this is the Sweet-Parker reconnection, and this is where you, the reconnection time you can have in reduced MHD simulations with plasmoids. Still, this time is higher than the experimental results, and for this you need a further step, which is the inclusion of these two fluid effects, which were already mentioned with the correct drift scale, and the inclusion also of diamagnetic effects. Without diamagnetic effects, this reconnection might be even too fast as compared to the experiment. Okay, now we move to the second example. We move to more external surfaces in the tokamak, where we see terrim modes originating from reconnection appearing regularly when the plasma pressure is high enough, so the plasma beta is high enough. And this has been related to the destabilization of the terrim mode through a neoclassical mechanism, so-called, which is related to the bootstrap current. The bootstrap current is a current in toroidal systems which you get when you have a pressure gradient, and which you usually do. And now the important thing is that in a reconnected region, the particles move fast along the field lines, and so in general they tend to flatten the pressure. This is something you can measure particularly well in the electron temperature, for instance, as you see here. And this so flattening of the pressure means a perturbation of the bootstrap current, which you can show to be usually destabilizing, leading to further growth of the island. And in this cartoon, you see why we terrim modes are unwanted guests in general in tokamaks, because this reduction of the pressure decreases the energy content of the plasma, of course. If you think a second about this, this cannot be the whole truth, of course, because you can imagine that there are effects that lead to incomplete flattening of the pressure, like finite transport across the island or finite orbit width. This is particularly true when the island is small compared to this transport scale, so to speak. And indeed, in tokamaks, you usually see that in many cases, you see that neoclassical terrim mode appears after a trigger with a finite amplitude, indicating some threshold for the destabilization. And so the stability of small islands is a very active topic of investigation. The way we approach this then in experiments is usually to analyze the process in terms of the modified Rutherford equation. This is the time evolution of the island width in time. This is the delta prime parameter introduced by Daniela. It's related to the equilibrium current profile, and this is the bootstrap current contribution, and there are many others. If you plot this growth rate as a function of the island width, you see that if the island is large enough, as we were saying, this bootstrap drive can take over and lead to a growth. But if the island is small and we have this stabilizing effects, then you need first to bridge this threshold in order to have the mode to grow. This is not the only situation. Of course, you can have a situation where delta prime is positive. You have a current-driven island, so that can really be spontaneous reconnection, as introduced by Daniela. And this has been reported in the experiments where you can observe a first phase of growth of the island from 1 to 2, and this is attributed to the delta prime, so to the equilibrium current profile. When the island is large enough, you see a second phase of the growth of the island, which is ascribed to the bootstrap current modification, and this is something you can model with this modified Rutherford equation. A similar situation we are investigating at the moment, more theoretically than with experimental evidence, is a similar situation where this seed island, which then can be driven unstable by the bootstrap current, is given not by delta prime, because here it was negative, but it's driven by a coupling, so with nonlinear coupling of small-scale turbulent instabilities. Just to mention that this, in terms of simulations, we are now getting in a position where we can perform gyrokinetic simulations of this process. They're still quite expensive, though. And with this, I'm already getting at my summary. also answering one of the previous questions, I would say one typical thing in tokamaks is that the geometry is really a very important constraint on the kind of reconnection events you can have. But otherwise, there are several things which are in common with the general problematic of reconnection-driven, spontaneous, multi-scale. I can say in all these cases, we have significant progress in understanding that there's many things to do in terms of resolution and simulations and all these things. And I will just mention, concluding, that we have the possibility to influence these reconnection processes. I have no time to explain this, but this is an important point to keep in mind. We are not just left with these instabilities. We can do something to control them. Okay, that's it. Thank you.
Thank you, Emanuele. So can you please just, for the audience, recall quickly delta prime, because you speak a lot about delta prime. And yes. Can you say more on this delta prime about the theoretical value in the modern tokamak?
Yeah, so in the meaning of this delta prime is, you have seen, this is related to the profile of the current of the current and the equilibrium current, let's say. It is so delta prime is a subtle thing, because strictly speaking, in a torus you have toroidal coupling, so it's not that easy. But if you think in terms of the Rutherford equation, people usually estimate, suppose in a large tokamak, usually this gradient is small, and you can even take a first estimate of the delta prime from vacuum, just so to speak, just in terms of a vacuum magnetic field, and this turns out to be negative. And so people assume that this current is negative, so this delta prime is negative, usually in tokamaks, as you were saying. But of course, you have, in particular in tokamaks like TCV, where you have a real powerful control of the current profile, you can drive your current profile in such a situation where you are in the opposite case, so you have a positive delta prime. And this they do several in several different contexts. So it looks like it's a robust way to they can control it and have it positive.
Thank you, Emanuele. So now I will give the floor to Anta Oji from PPPL and Princeton, and he will speak on the laboratory study of magnetic reconnection.
Yes, do you hear me?
Yes, we can hear you, but we not see your screen yet. Okay, we can see your screen.
Okay.
Thanks.
My full screen or the other screen?
Your full screen. It's okay. Oh. Your presentation.
Okay, very good. Thank you very much for the opportunity to speak to large audience regarding this important, interesting subject. My talk will be very short, but I'm going to focus on the laboratory study of reconnection based on the two review papers I listed here, and then also the 3 white papers we submitted to US Digital Survey in the past few years, summarizing major challenges and opportunities in the future. So we can move on. Okay, so the progress of reconnection research in the past 70 years can be simply divided into 3 phases. The first phase is from 50s, from last century to 90s, focus on MHD understanding of reconnection, and on the topic of the reconnection rate, or fast or slow. And it's motivated by solar observation, mostly solar flares, and for example, by Yoko satellite, and also motivated by laboratory fusion tokamak sawtooth origination observation in the 70s. But on the other hand, basic plasma experiment like LPD or MRX that I'm going to talk about will be also starting in the 90s, which I'm part of that. And that is a move on to the second phase from MHD to kinetic physics, ion electron kinetic physics. Not only the reconnection rate, but the detailed dynamics ion electrons, and based on lots of in situ measurements mentioned before by Junior in this webinar, for example, by the cluster and MS satellite. In the meanwhile, basic plasma experiment also moved on to the kinetic research based on MRX, and the VTF at MIT are now T-Rex in Wisconsin. The phase 3 actually already started to trying to bridge the two scales, fluid scale, MHD scale, and the kinetic scale simultaneously. We call it macro scale. It started in 2000s and still ongoing. Hopefully, we can resolve in the coming decades. And then not only just macro scale in terms of rate, but also energy problem, how energy is converted from magnetic field to plasma, how onset of reconnection can be understood and predicted. So the macro scale observation by the proposed plasma observatory in Europe, and also the macro scale computing. I don't have time to talk about this, but it's reviewed in the review paper I mentioned. Also, the upcoming the macro scale plasma experiment, called a FAIR, is upcoming to attack this problem. So this is a very short, non-exhaustive list of the past experiment, ongoing experiment on reconnection. It's too many to read. I simply point out it started from 70s, 80s, 90s, even nowadays, new experiments keep coming up. I don't have time to cover, but to highlight MRX or magnetic reconnection experiment, T-Rex in Wisconsin, and a FAIR, I've been mentioned only very, very briefly by this short webinar. So magnetic reconnection experiment is a picture from side. You see the left and right are symmetrical. And if you're looking inside, you have coils inside vacuum chamber to create a magnetic field geometry left and right symmetrically. And if you drive the coil current in green in parallel, then you get the cortical structure magnetic fields. When the plasma present outside the coil, when you reduce the current in the green coil, you're going to pull field line back to coil. We call it pull reconnection. Force the field line go around two coil through reconnection becomes a field line go around only one of the coils. So that's a reconnection we call it under our control, because we know where and when a reconnection happens, but also with extensive diagnostics, which I showed here as example, 90-channel probe array, the major magnetic field profile evolution when this reconnection is driven or induced. With this, we can quantitatively study reconnection process. First thing we have done is really check this, the so-called three-parameter MT model work or not, and the answer is indeed it works. So on the left, we show when the mean free path is very short compared to current sheet thickness, everything becomes conjugal, and the major resistivity is consistent with the Spitzer prediction, and the MSD resistive ohms law works very well. In that case, the three-parameter model indeed works between measurement and predictions. So this is a very satisfactory verification of the long-standing model of the reconnection. But if you move to the right on the left figure, when mean free path get long compared to the thickness of the current sheet, the generalized ohm law has been used or been introduced before. Not only resistive term, but the other terms I don't have time to talk about, the kinetic effect or total effect will need to be taken into account, which is more important than resistivity. In this case, ion electron behave differently when approach current sheet. For example, the right-hand side is measured all-plane cortical structure magnetic field due to a differential flow between ion flow and electron flows. So this is precise. It was predicted by a simulation and has been verified in experiment. So with this measurement capability, we can do really one-to-one comparison with space measurement. For example, the first one with European Space Agency's cluster measurement. At the left, we compare the cortical structures, and at the bottom far, due to the only 4 satellites of this cluster, you need a statistical accumulation, not of the data, but properly processed, so that you can see also a cortical structure, like a red, black, and red, consistent with the structure if you are oriented correctly in the same geometry. On the right-hand side, the in magnetic reconnection plane edge fields has been measured by potential in the MRX, and have ion flow be driven by the unmagnetized ion can be driven flow fast due to the pressure electric field from one potential to the other potential. That can be compared one-to-one to the cluster measurement by two satellites, one close to the X9, one far away. They show similar structures. Even better comparison can be done between MRX and MMS. So here is one more recent example how main field profile according to cross current sheet compare between MRX and MMS, and at a current sheet, a current density profile. But for the electric field, there's still a factor of 10 difference between two measurements. This is a question we are currently trying to understand. And the right-hand side, we compare the so-called asymmetry reconnection. One side is different from the other side. And this is really a MRX measurement. And this is, if you take cuts of a current sheet, you get the various profiles, and it can be compared with the MMS measurement, almost a one-to-one again. So we are getting very close to the quantitative comparison between two measurements, even though the physical scale is very largely different, as we know. So in addition, of course, we always compare with theory. This is a two-dimensional particle in cells measurement comparison. Left is measurement, half the quadrupole structure, outer plane magnetic field, and right is the prediction of the simulations. On ion scales, they match very well and almost into the details. But we have found there's disagreement for electron scale on MRX. And this has been a more than 10-year mystery, but interesting new result come out of T-REX and Wisconsin that they have found agreement between the 2D peak simulation and their experiment. So we are in the middle trying to figure out what's the difference to make two cases, and they're getting very interested. So now we have one limit, conventional MHD model called phase 1, like a phase 3 Parker, and it's good for large plasma, but predicts slow reconnection because Nucleus number is small. But on the other hand, the phase 2, we have a kinetic model, works very well. Ion electrons have quadrupole structures. They predict faster reconnection, but only applicable for small plasma. You have kinetic, give you a faster reconnection. So the question is, how do you combine the two models together, save consistently into one model to explain the fast reconnection in large plasma or non-Nucleus number commonly found in space astrophysics? This is a multiple scale challenge for the phase 3 research. So there's two multiple scale idea right now being proposed. One is the plasma instability or being discussed. When current sheets getting too long, they break down by tearing instability, which can be forming new current sheet. The new current sheet can be further be unstable, forming further smaller scale current sheet. It eventually get down quickly to the kinetic scale that we want to have, or by 3D turbulence. And we know turbulence is another multiple scale process from large scale to small scale. So two ideas are competing, and we don't know which one is right. In the plasma instability, based on plasma instability, you can construct so-called reconnection phase diagram in the parameter space Nucleus number and the plasma size, normally the ion scales. So you can not only a single X9 regime we have done so far, both conventional or kernel-less. When plasma is sufficiently large or conducting, we have multiple X9 regimes, 3 different ways: globally MHD and locally kinetic. They couple through the plasma instability. And the various astrophysical reconnection events can be plotted into space. They are across many places. For example, here is main sphere, here is ether, TFTR, MST in very kernel-less limit. So in order to reach to the new regimes, we have designed a new device called FAIR, trying to reach the new regimes have multiple X9s. So from the current MRX1, which is a small box here, trying to do the stage 3 energy level of the FAIR. By the way, FAIR is standing for Facility for Laboratory Reconnection Experiment, and the hope is trying to provide access to the new regimes, or 5 different regimes by one machine. So this is a machine being proposed and being constructed already in Princeton. This is stage 1 capability with a 0.8 megajoule. Right now it's being upgraded to a full stage 3 capability with 6.9 megajoule energy. And then we're expecting by end of this year, it should be online. And everyone in the world should welcome to come to use. So with this, I want to summarize. We have a map, a roadmap. Sorry, it's not a fusion roadmap, it's a reconnection research roadmap here. Have the phase 3 that we want to attack multiple scale physics between fluid globally, local kinetically. And this final step will help to understand reconnection. And plasma instability is being proposed, and field project has been constructed to attack the problem. The particle acceleration, we didn't get a chance to talk about this. It's still largely unknown by multiple scale reconnection. It's being discussed. It started theoretically a lot, and they are proposed like a part of edge field acceleration, Fermi acceleration, and the Bertrand acceleration mechanisms. And which one is working under what conditions? Well, we don't know. Onset, we already been discussed, and it's a very important challenge because we want to make a forecast about space weather event like solar flare, and also like disruptive phenomenon in tokamaks, and when such a reconnection can happen suddenly. And this is our challenge. And here's 3 references for your future reference. Here is a NAS diagram I want to emphasize. And from space and laboratories, particle sales mission, we are attacking kinetic scale. From the sonar and astro observation, they are very global. They are fluid MHD. And it's also a large fusion experiment is also in MHD. They are approaching to larger scale. Hopefully, we can bridge the gap in between to attack multiple scale particle acceleration onset. So my hope is we can solve the problem together by close cooperation between basic plasma physics community, fusion community, space physics community, solar physics, astrophysical community together. Because without one or the other, I don't think it's easy. Even combine all, it's still difficult. And then my hope is that work together to solve problem in the coming decades. Thank you very much.
Thank you, Antao, and also thank you for your last message about the importance to work with all communities. A question from the audience. So in the flare, what is the order of magnetic field magnitude and also the order of plasma density?
Yeah, so the flare, the strategy is using low temperature plasma strategy. Main field actually very strong, can be as large as a few kilogauss. Actually, design value is 5 kilogauss, and it's almost like a fusion. But plasma density is relatively common, 10 to 19. But temperature, we want to be very low. Why? We want to put lots of probes so that it can measure main field evolution like we did in MX without being too hot. If it's too hot, we'll lose the capability to measure main field and also other parameters. So that strategy is using strong main field, moderate density, but low temperature.
Okay, thank you.
Okay.
And so we arrived to the last speakers.
Maybe
Jonathan?
I can just ask can I just ask a quick one?
Of course, go ahead.
So I've heard from people who run initial value codes that we know quite well in fusion community that plasmoid simulations are very challenging because of the scales involved and the changing scales involved. So could your experiments be used to try to benchmark or try to nail down the physics of these simulations?
Yeah, this is our goal, and we want to cover both global MHD physics and local important kinetics simultaneously in one plasma, and by not just creating it but also measuring it. So I didn't get a chance to discuss. We have constructed probe arrays, and as small as an electron scale, a few millimeters resolution, but covering a meter long MHD scale simultaneously in between a few centimeters, of course, ion scale. So have 3 scale by 1 measurement and many locations in space, and it can be arranged 2D or 3D. So it depends on problem, we can move around the diagnostics to capture very detailed 2D measurement or relatively coarse but 3D measurement. It depends on problem. For example, the sawtooth problem or the mechanical, say MCO1 problem can be conceived because we can generate not a tokamak, say a center coil carries the current, have artificial QCO1 surface that can be. We have a proposal actually being cooked right now, but we haven't formally proposed. But you're welcome. We can discuss. No.
Okay, thank you very much. Yeah.
Thank you. Thank you, Antaouf. Thank you, Jonathan. So we can move to the last speaker, Miriam. So Miriam Ahmed from DIFER at the Netherlands, but she's moving now to Texas University. And Miriam will present a talk on microtearing turbulence in H-mode plasma. So Miriam, you are welcome to present your talk.
Can you see my screen?
No, not yet. We can see your webcam, but not your slides. Okay, can you just switch, to utiliser un diaporama? Yes, okay, we can see your slides. Thank you.
Okay. So good afternoon, I'm Miriam Ahmed. I'm going to talk about the turbulence, the microtearing turbulence in the H-mode plasma. So as you know, the main scenario for heater is a high confinement mode, the H mode. And this mode is characterized by the formation of the pedestal region. In this picture, I just show you I try to explain what is a pedestal. So 0 is the core, 1 is the edge. And you can see in the S, steep gradient develop, and the steeper the gradient, the higher the confinement. So the prediction of the height and the width of the pedestal is very important for the optimization of future fusion device like ITER. But the pedestal is limited by different kind of instability, and I study and microtearing mode is one of these instability. So the first reason why I study microtearing mode, here I show you a fraction of the jet pedestal as a function of beta, and different kind of instability are developed in the pedestal, like microtearing mode, electrostatic drift wave mode like ETG, ITG, and the kinetic ballooning mode. And microtearing mode are found unstable in the jet pedestal from the top to the middle of the pedestal. So the objective of my work is to better understand the role played by this micro instability. So here I show you three situations. The ideal situation was the electron are perfectly confined, but if you apply a magnetic perturbation, the magnetic field can break up and reconnect to form magnetic island. And if the magnetic island overlap, you can create a stochasticity of magnetic field, and an electron perfectly confined in the core can reach easily the range. So microtearing mode can produce a transport due to a stochasticity of magnetic field line. And using a random walk, we can predict the transport due to this micro instability. And the main point here is if you apply a very low magnetic fluctuation, you can produce a transport. And microtearing mode are found unstable in the several tokamak configuration, jet, ASDEC, spherical tokamak. So this is why my objective is to better understand the role played by this micro instability and to evaluate the transport. So before to continue, just a few words about microtearing mode. So this is a classical picture of this mode. This is radial, the current, radially, and a current developed inside the current sheet. And if you solve the Ampere's law, you can see far away the resonance surfaces are parallel GK as an exponential minus KYX. And we assume for the development of theoretical calculation, we assume that A parallel is constant in the current sheet. So microtearing mode is an electromagnetic instability destabilized by strong electron temperature gradient. It's a localized mode around the resonance surfaces with the tearing parity. So this mode can play a significant role in the plasma turbulence and transport and can affect the confinement. And microtearing mode can lead to limit the height and the width of the pedestal. So for this presentation, I just want to present you briefly the theoretical calculations and linear gyrokinetical simulation of microtearing mode. I will present also very briefly nonlinear simulation, and I will finish by a conclusion. Here just came of the way I used to work. First, if I want to understand microturing mode, I need to develop a theoretical calculation. So I need to do some assumption. And to do some assumption, I use gyrokinetical simulation because it's very simple in gyrokinetical simulation to delete, for example, magnetic drift or electric potential is very simple to evaluate the effect of this physical parameter. And then in the gyrokinetical simulation, I use experimental data, and at the end, I try to compare theory and numerical simulation using experimental data. So very briefly, for the theoretical calculation, I wrote the Ampere and Poisson equation under a variational form. I want to express the parallel current in the current sheet, which is the integration of the distribution function in the velocity space. And so here, this is the Fokker-Planck equation. And this equation, I had the missing physical parameter, like the collisionality, the magnetic drift, and the electric potential. And at the end, I found a system of equation. The system of equation looks like a kinetic MHD equation, but here the speeder resistivity is replaced by the kinetic conductivity, and this parameter the beta, is related to the physical parameter. Now, with this system of equation, I can study, for example, the impact of the temperature, the density, the safety factor, and also the collisionality, the impact of this physical parameter on the microturing destabilization. And I solved this system of equation using an eigenvalue code called solve-AP, and in this code this code compute the omega and gamma solution, the growth rate and frequency solution of this system of equation. And the objective is to compare the theoretical calculation with the gyrokinetical simulation. So now I just want to show you a linear simulation, gyrokinetical simulation of the pedestal at different radial position from the top and the bottom of the pedestal, and to see that in the pedestal, different kind of instability can develop with a comparable growth rate. And you can see we found KBM, electrostatic drift wave mode, and also microturing mode in the middle of the pedestal. So microturing mode are unstable in the middle of the pedestal for this shot. And here, this is the mode of frequency. So it's very important to note that when we try, it's very challenging to study the pedestal region because there is different modes with a comparable growth rate, and experimentally in the pedestal we have only few points, but we use a very smooth profile. And if you change a little bit the slope in the pedestal, you can easily change one parameter. And for example, if you change a little bit the electron temperature gradient, you can destabilize easily microturing mode. So we need to be very careful, and also to check, to do a lot of convergence test and check the numerical resolution for this mode. So now I try to compare the solve-AP, so theoretical calculation using the eigenvalue code with GEAN, but I use a very simple version of GEAN close to my theoretical calculation. I use an effective magnetic drift, the psi-constant approximation, a simple collisional operator, and also I delete the trap particle. And if I compare, so this is the growth rate as a function of the collisionality. And you can see we found a good agreement between solve-AP and GEAN code, but we have to improve the theoretical calculation by adding, by improving the collision operator, for example, or add a trap particle. So this work is ongoing, but it's very, so the simulation are very expensive and very long. So it's very, I developed this theoretical calculation is very important to have a predictive model for microturing mode. So now for the nonlinear part, I want to develop a quasi-linear model to have a good prediction of the transport due to this micro instability. And with this quasi-linear model, we can we could easily study the effect of the different physical parameters instead to run a long and expensive gyrokinetical simulation. It will take few seconds to have the result. So here, so this for the principal effect of magnetic perturbation is a modification of magnetic field line. So I want to develop a quasi-linear model, but for that I have to first to understand the saturation of this mode. And I run several nonlinear simulation to better understand how the mode saturate and the saturation mechanism to develop saturation rules. And I delete in the code in gyrokinetical, the electric potential, the zonal flow, zonal field to better understand their role on micro-Turing turbulence. And I see with this plot very briefly, we can see this two curve is without the electric potential and this four curve is with the electric potential. The main point is with and without the electric potential, the saturation mechanism are completely different. So now I try to understand the role played by the electric potential and then to at the end have a predictive transform model for micro-Turing modes. So just for the conclusion, the study of this mode is challenging because we have to improve we have to develop a theoretical calculation to improve it by adding to improve the collision, to add trap particle, to add physics, and to develop saturation rules and and at the end to have a predictive transform model for this mode. So as I said, and numerically it's challenging because due to the small scale nature of this mode, we need a very high resolution and do a lot of convergent tests and yeah, because there is a lot of kind of instability with comparable ghost weight in the pedestal region. So thanks for your attention.
Thank you, Myriam. In your talk, you speak about various instabilities, so KBM, ESDW mode, micro-Turing mode. For the space plasma audience, can you say what is the difference between those instability and do this instability leads to magnetic reconnection or not? If you can say more.
Yeah, like but the drive is different from micro-Turing mode and like ETG and ITG kinetic ballooning modes. The drive are completely are different, and this mode cannot lead to the magnetic reconnection. But it's a little bit complicated because sometimes we can find ETG with a Turing parity. It's possible to is an interchange mode with the Turing parity.
Just to maybe it's not necessarily to enter in such details, just to give the feeling to the space plasma audience that in tokamaks we can have various instability, and what is the energy drive in fact for micro-Turing mode, it's the currents, but what is usually the drive for KBM, ETG, ITG, and so on?
For ETG, ETG is the electron temperature gradient, ITG is the ion electron temperature gradient. For KBM, it's sensitive to the beta.
Okay. Okay. So thank you, Myriam. So I propose now to go to the panel discussion and to discuss about various questions to all the speakers. So maybe all the speakers should open their camera. So thank you. So there is many questions, and I probably I will not able to ask all of them. So I will try to do it maybe in like, you know, going to basic question to more further questions. So for example, on basic questions for Antao, you show that you have make some measurement of magnetic reconnection, and you have shown some picture of your experiments with 4 fixed coils. So that means that I suppose you have you do a measurement of the magnetic field, and so this means that the place where you put the coils and the probe should be the place where you have magnetic reconnection. So can you say more about the measurement itself of magnetic reconnection in a laboratory plasma?
Yes, like Junior has been talk about so-called ion diffusion region, electron diffusion region. In MHD, is only one diffusion region, which is the resistivity. Remember the current sheet MHD, but in ion electron plasma, you have 2 diffusion regions. One is ion diffusion region, one is electron diffusion region. The ion diffusion region means the electrons stay magnetized, ion become demagnetized. They can move differently between ion electrons. So when I'm showing you on ion scales, there are a few centimeters in space in size. We can place multiple pickup coils and in many locations, the one reconnection plane to measure the two-dimensional profile at function of time. In fact, we can see the movie every discharge, how field line coming in, how field line goes away, and it has this quadruple structure shows up during the middle. So on ion scale, we completely captured the spatial and time evolution. On electron scale, in the meanwhile, it's only a few millimeters. John has asked the question, and we are challenging ourselves, and we're trying to capture the outer part of that. May not be as resolving as ions, but we are on the electron scale already. So I'm hoping, I hope that we can do better in the electron scale, so that they can do, because the electron, as we know, is more important sometimes than ions. And then, like, animals transporting tokamaks is lots of trouble of the electrons. Ion can be classical. Here, the same problem. Without resolving electrons, we don't know the physics very well. But like a MOS measurement that Julia has measured is really on the electron scale. This is the advantage of space. And the 10 kilometer is the electron in the magnetic tail. You have lots of resolutions, maybe too much resolutions. You measure all three-dimensional electron distribution function at function time and space. So you have huge kinetic information that are not available by laboratory experiments. So I'm not saying we can resolve everything. That's why we have to work together. Is that okay?
Yes, thank you. And from the fusion side, can you say more, maybe Emmanuel, about the way of measuring magnetic island and magnetic island sizes in tokamak?
Yes. So what you have seen in the first, in the case of reconnection events, that were soft X-ray cameras. So they measure radiation in the soft X-ray range. What we do usually for Terry modes, so you see modes in the magnetics. So you have coils, pickup coils that measure magnetic perturbations, and you can resolve them by in Fourier space, so to speak, with respect to the poloidal and toroidal mode numbers. I think the best measurements of islands we have are usually in the electron temperature with the electron cyclotron emission. In this case, you measure, that was the one picture I presented where you see this flattening, for instance. This is one way to, to my knowledge, this is the most robust way to assess the presence of the mode. Usually you need a combination of diagnostics, because you see some features in one signal and other features in other signals. Yeah. So that is, sorry, just to conclude, this is a very important point, because where we are lacking knowledge theoretically is unfortunately exactly the region where we are lacking experimental knowledge, because when the islands, let's say, are below, let's say, a width of 1 centimeter, so more or less, it becomes very difficult to detect them, and that's exactly where we don't know what they do.
Okay, thank you. And Daniela, you mentioned at the beginning of your talk that magnetic reconnections can go to magnetic chaos. Miriam also shows some stuff, some picture like that. So my question is it possible to see experimentally this chaos? Or maybe Daniela, or maybe Emanuele, or
I mentioned also reverse the field pinch, where chaos is encountered every day, I guess. So yes, it is possible to see it in some way, yes, definitely. And it actually, chaos comes into play when you consider the third dimension, which is an aspect which is really, really important, because 2D description is good when you have a strong guide field, but if you have only one magnetic island, as soon as you consider a situation like also in a tokamak can occur, and you have maybe two magnetic island chains, and they interact non-linearly, well, at that time you will develop magnetic chaos. And this opens a huge amount of question and of investigations, because nonetheless you have chaos, you can have order structures, you can have order current sheets, and in the magnetic chaos. So understanding the role of the hidden structure in the chaos, it's really important also for tokamaks and for thermonuclear experiment. So I can go on for a long time talking about chaos, so you have to stop me.
But I suppose the main experimental signature in a fusion device would be extremely poor confinement over quite a large region of the machine, right? So very, very poor, essentially no gradients in the plasma, and extremely poor.
Exactly. I think the major demonstration of stochasticity, of magnetic stochasticity, when you induce a disruption, which is usually attributed to the superposition of many chains of magnetic islands, and this leads to a relatively fast quench of the temperature because of this. Yes, I would agree. And I could say also the other way around. There are situations where in simulations you see a lot of stochasticity you don't observe in the experiments, and that's also a very nice, interesting point, let's say, in the comparison between the theory and the experiment. Yeah.
Yes, but for instance, sorry Magali, if I can add a small thing, is that for instance in the reverse feed pinch, we have studied in the past the coincidence of Lagrangian coherent structures, I mean of the hidden structure in the chaos, that coincide with the temperature barrier that forms in the simulation and in the experiment. So chaos does not mean always that you have a uniform distribution of quantities. That's an important aspect that we have to keep in mind when talking about magnetic chaos.
Okay, so we have other questions from the audience. So one question is, what kind of diagnostic is used to resolve the electron scale? So in the answer, you have to be aware, and you have to pay attention of the fact that electron scale has not the same meaning in fusion plasma and in space plasma. So is someone want to answer?
I can maybe reply for the space part, but I don't know whether, yeah, this is the whole answer. I guess I will need input then from the others. But yeah, I mean, from MMS, one major point was the instrumentation that they developed. That was very similar indeed for like the ions and the electrons. So you have this analyzer that are actually put on. So the structure of the spacecraft itself is a octagonal, I don't know how to say in English, but it has 8 sides. So there are these instrumentations that are able to let's say, collect the particles on 4 different of those. This means that the measurement is now disentangled with respect to the spin time of the spacecraft, because the spacecraft is also spinning in space. And this is what allowed this total, let's say, revolution in terms of resolution, going from cluster that has a resolution of the measurement, for example, of the distribution functions that were related to the spin time, about 4 seconds, with respect to MMS, where we have now a resolution of 30 milliseconds for the electrons and 150 milliseconds for ions. And as Antao was pointing out before, this is something I couldn't fit in my talk, but in space we are measuring the 3D distribution function. So resolving in, let's say, time and space, depending on the position of the spacecraft. This is very important to assess the kinetic physics of the plasma, of course. And this is something that, at least in the previous years, was not so easily achievable with the laboratory plasma, for example. Now maybe Antao can tell us that let's say these things are changing, but it's definitely something that is very important in space. So this is something I haven't shown, but we have time series also of distribution functions, for example, for the electrons, 30 milliseconds, which means that we can know the dynamics of the electrons really in the kinetic sense, even within the electron diffusion region. So
yeah,
I don't know if this answers, but yeah.
One physics interesting point can be added here is in the plasma physics classes or textbook, we always assume the background Maxwellian, then do a little observation like a delta F. That doesn't work in space because during the reconnection, the distribution function is very crazy. And nothing looks like it's Maxwellian, have plus alpha. The whole thing have huge beam one way, have ways of diagonal terms, very important thing. So it then becomes really hard to model the plasma. You cannot assume Maxwellian. So what you can do, well, it has to be full kinetic in order to understand a problem like this. However, and if you do that, it's very expensive numerically. So this is a challenge for numerical research. How do we model like a not nasty, so nasty plasma like that during the violent reconnection event? In TalkMap, the gyrokinetic is a good approximation with strong dye field. The how good it can be, the question can be raised. For example, I don't have more answers. I will add one more interesting physics. From the laboratory side, I see space data. Wow, it's very crazy. So that's why I'm bringing up the topic here.
Thank you. Maybe quickly for the fusion size, Julia, you want to?
Can I just say, know that in the slide that I sent you, there is some extra slides, and I put one of these, let's say, iconic nowadays.
I don't know if you can see my screen.
You cannot. No, I can't. But it's not important. But just to get some visuals to what Antao just said at the very end of the presentation.
Julia?
Yeah. So if you go at the very end, there are some extra slides, and I didn't have the time to show. Yeah, there is one, this 58 slide that should show also some relatively crazy distribution functions. And so you can see that those are recorded at different times. The one, the number 58, yeah.
I cannot see the 58. This one.
Yeah. So these are, for example, 3 different perpendicular plane of the distribution function. So we have the 3D, but in order to visualize it, we select the proper coordinate system, for example, perpendicular and parallel to the local magnetic field, and then project in the 3 perpendicular planes. And something that MMS highlighted even during the one of the first observation was the presence of the so-called crescent distribution function that were showing that the electrons are performing these meandering orbits that were well known theoretically, but this is actually showed in the data that the ions are demagnetized and they perform this kind of orbits within the electron diffusion region. So this was very nice to see. Thank you for sharing the presentation.
You're welcome. So, and for the fusion size, maybe quickly, as said by Emanuele, in fact, we are not able to measure a magnetic island under the centimetric size, and so electronic scales is very small. It's less than 1 millimeter. So for the reconnection phenomenon, we are not able to have a diagnostic at these scales. So we can go to other questions. So we have a long one. I will try to summarize it. You said that in tokamak we have different instability like king SAO2, steering mode, MTM in pedestal. And this instability can link to the, so this is a question, to the same reconnection event, yes or not? And the question also is, are this instability behind the reconnection, or it is a role of the resistivity or Hall effect? Alors, Hall effect does not lead to magnetic reconnection. So this is the questions.
Yeah, maybe. So for micro-Turing mode, the mechanism leading to the magnetic reconnection is very difficult to identify. It's not easy to understand how the mode is. The destabilization mechanism is very difficult. It depends on physical parameter, and I think in the region, I feel like if you are in the core and in the pedestal, the destabilization, it depends on the collisionality. The collisionality, the destabilization of micro-Turing mode depend on the collisionality in the tokamak. If you're in the core or in the pedestal region, is very different. And what is the question then?
The question is finally, does the resistivity and the Hall effect, so Hall effect I do not really understand because Hall effect cannot lead to magnetic reconnection. Hall effect can just accelerate magnetic reconnection if you have already magnetic reconnection, but it is the role of resistivity to give birth to magnetic reconnection, or it is the role of the instabilities. So maybe if I can comment this question. So it's a good question, and there is not. It is a point of view. So you have many things. First, you have in the Ohm's law, as shown by Daniela, some mechanisms that allow magnetic reconnection, like resistivity, electroinertia, pressure, anisotropy of the electronic pressure. Hall effect does not lead to magnetic reconnection. So this allows magnetic reconnection. And then you have instabilities like tearing, kink mode, micro-tearing mode, which is different to tearing mode, that will let grow the magnetic island.
Yeah, exactly. I think this is a peculiarity that there is a very interesting physics about the reconnection process. For instance, you take a tear in the classical tearing mode. You need this drive to bridge this threshold, and this can be a sawtooth crash, which has after the crash still a so-called post-cursor, so a perturbation which survives for some time, which might be of ideal kind and pushes, has a component that pushes on the, not on the q=1 where you have the crash, but for instance q=2. It pushes the plasma for a sufficient long time that this can become a resistive instability. This is probably also faster than sweet Parker time. But the funny thing is that in the fusion community, we don't spend so, it's very interesting from the basics point of view, but in the end, we are, if you think in terms of a reactor, we want to know why then this island that you formed this way grows and how big it will begin, it will get. And this is quite unrelated to the mechanism that produced the island at the beginning. It's just there are some other nonlinear, like the bootstrap destabilization and so on, they take over, and we look mostly at them because we want a reactor to work in a reasonable way with a significant energy confinement. And but there are studies also about this seeding phase, because they relate it to the way you can induce ions from outside through external coils. It's a quite similar mechanism in the end.
Thank you, Emanuele. So we go back to stochasticity. So a question, there is no theorem in the question. Is there a theorem saying that chaos stochasticity implies disruptions?
Say it again, sorry.
Is there any theorem saying that chaos stochasticity implies disruption?
Mathematical proof?
Yeah, I think
mathematical proof they want.
I think it's from the mathematical point of view, because I see the person who asked the question, and so probably it's from a mathematical point of view.
Certainly, experimentally, this is the case. So we see in experiments that where there are multiple islands, well, one thing that we have in the experiment in tokamaks in particular is that the plasma is rotating. We didn't really talk about that very much today. The plasma tends to spin because of axisymmetry, and there can be a shear in this flow as well. And this tends to ensure that if you have magnetic islands on multiple surfaces, these rational surfaces that were described today, if there are multiple modes, then they tend to be separated. They don't couple so easily because of this shear in the rotation. But under certain conditions, the plasma rotation can be killed, or the shear in the rotation can be killed. And under those conditions, the magnetic islands can become coupled to each other. And then when you tend to get a damping in the flow, you get something experimentally known as mode coupling, or you can get modes which really then cover the entire plasma, and then you do almost exclusively get disruptions. You can get disruptions because the islands become so big, or you can get disruptions because when the island become big, then you can get a massive amount of impurities that come into the plasma, and this itself is a danger as well. So certainly empirically, this is definitely observed.
Thank you. A question for Giulia. You speak about turbulence and turbulence-driven reconnection in space plasma and in your observation. Can you say more about that in terms of where does the turbulence come from? What is the nature of this turbulence, and how this turbulence can drive magnetic reconnection?
Okay, yeah, thank you for this question. So yeah, what we see in general, so I tend to say this because it's easy to be, let's say, to mix the two things, but there are what we can call like the reconnection driven by turbulence. So you have a turbulent medium, like the magneto sheath is the example that I brought up, and there you form current sheath and they reconnect. And this is something that has been studied for a very long time, and still we have open questions. The other, let's say, scenario that we might have is that we have a relatively larger scale reconnection. You can think about the magneto tail or like sort of a larger scale current sheath, and we see that reconnection is induced by reconnection. Turbulence, sorry, is induced by reconnection itself. So this turbulence can be observed, for example, in the outflow region or in the reconnection jet, right, where the plasma is accelerated. This is something that, at least from the point of view of observation, is not very much, let's say, investigated or fully known. So there has been some papers, specifically by Robert Ergun at LASP in Colorado and his team, that they identified a couple of events in the magneto tail where they would observe the electron diffusion region even, so a crossing really through almost the reconnection site, but then regions of very, very strong magnetic field fluctuations and velocity fluctuation that they resemble sort of a turbulent plasma. So what turbulent is, how we characterize turbulence, is also something that can be problematic in space, because you only have the knowledge of the passage of your satellite through the region, we tend to have relatively short intervals in the magneto tail, which is not, for example, the solar wind where you can cross a turbulent medium for hours. And so this poses a lot of challenges in fully characterizing the turbulence. So this is an open, let's say, area of research in some way, but what has been observed is that definitely we have a very strong acceleration of electrons and ions. So this was shown, for example, in the plot I showed just for a few seconds. So this indicates that the presence of the turbulence can actually have a large-scale even effect, like accelerating larger amount of particles and changing the overall energy conversion by the reconnection. But yeah, I cannot say maybe more than this, because again, we probably need more events and even possibly statistical studies on the effect.
But on the mechanisms itself, you mean that finally the turbulence flow will bring close together magnetic field line to let the magnetic reconnection occurs? This is a mechanism.
So this is something that would be a consequence possibly. So how I imagine it is like we have a large scale current sheet, a little bit similar to what maybe Antao showed at some point. There is a reconnection, which there is a turbulence which is within the outflow, and this, depending on the scale, could allow the presence of smaller scale current sheet that they reconnect on their own. So I don't know whether I'm explaining myself, but it could be sort of a chain, as Antao was showing, sort of a fractal situation where if you zoom in, you find more reconnection. But yeah, maybe Antao has something to add.
Yeah, that's an interesting, actually, current research area, the interaction between turbulence and reconnection in the space side. There are, say, MHD turbulence that cascade down to the small scale, kinetic scale, then reconnection being part of dissipation and modify the spectrum energy dissipation. So here, I do have a question for the fusion side. It seems that micro turbulence could be due to, say, tearing instability, or micro tearing instability, or drifting instability. Is it possible that two can interact together, to generate, some it's a mixture of the like a micro tearing, kind of a way, and also electron drifting, drifting instability that typically people think about the transport problem. Do you have a case that the two can be interacting like in space?
I don't know who wants to answer, Myriam, Emanuele, or so I will go. So you can have in fusion plasma, what is observed in simulation is the fact that turbulence can accelerate the growth rate of the magnetic reconnection structure by nonlinear interaction. And so the source of the growth of the magnetic islands is taken from the turbulence. However, this has not been observed in experiments yet in tokamak, and it's still it's ongoing work. So.
Oh, sounds like it's ongoing work too. Okay.
Yes, yes. And for the micro-tearing mode turbulence of Myriam, as far as I know, there is no interaction with a large-scale structure. It's not just, but it's a drive taken in the electronic temperature gradients that will drive micro reconnection at ionic Larmor radius scales in presence of resistivity.
So it's more passive receiving, not the interacting. Okay, thank you. Yeah.
So there is a last question from the audience. Well, it's maybe you say more than me, but the question is lithium related to preserving high temperature? As far as I know, there is no lithium in tokamak, so I don't see really the point of this question. So I can say it again. Is lithium related to preserving high temperature? So I guess in tokamak.
Lithium, the element.
Lithium.
No, we shouldn't have lithium. We put in the panels to generate neutrons, but we shouldn't have lithium in the plasma, hopefully.
Okay. And one last question. So for Miriam, how does the micro-tearing mode driven in the pedestal depend on the local safety factor Q?
Yeah. I don't have the answer to the question.
I think it does not depend of Q profile since delta prime. I don't want to see delta prime because the drive of the instability is not like in tearing mode, the equilibrium magnetic field. The drives is due to the electronic temperature gradients. And so as you have a strong gradient of the electron temperature in the pedestal, this is why you have micro-tearing mode in the pedestal region in tokamak and not in the core. So it's not linked to the Q profile like in the large-scale tearing mode. So another last question. In fact, now I'm saying that this is like question. People ask question. So I will read it in live. There is the possibility to accelerate electron beam using magnetic reconnection created in labs. How much must be the magnetic field to do this study? So I think it's more for Antao. So
yeah, there are previously reported energetic electrons due to sawtooth reconnection in tokamaks. I think it's about more than 10 years ago from quite a few tokamak since then. Also ions, not just the electrons. And then nowadays, you can see a lot of, I see runaway electron is being a hot topic in tokamak research. And of course, it's not just the reconnection because the neutral voltage change and such, but reconnection is a part of that. So that physics, the acceleration of electron to high energy is a hot topic in space and astrophysics, and Junior has been mentioned. Especially in solar case, there's a so-called famous number problem. Certain solar flares have so much energy released by magnetic fields, they don't have enough electrons to carry the energy. So sometimes half the electron population becomes non-thermal, which is unheard of. That because usually we have like a very small number of particles becomes non-thermal. Only majority is thermal. In certain solar cases, some people claim, which is I don't verify myself independently, says like a majority or half of the electron has been non-thermal. So why? Well, because so much energy being released by magnetic field due to the connection in the very quick time scale, and not enough energy, a particle out there to take care of the energy, and no time to summarize it. So you can imagine it's very so-called nasty again situation. But in tokamak, I wonder, in the not the sawtooth crash, in the major disruption, maybe similar. I don't know. We have enough measurement how much electron thermal normal maybe.
It's difficult. I don't know if they have really if the measurement can they see the peaks I was showing at each crash. You see clearly that there are electrons being accelerated. How many? If they can be quantitative, I don't know. But I remember simulations where if you repeat this very fast crash for ether parameters, you might really get runaway electrons because of the sawtooth crash. This is quite interesting. But again, this is something we should be able to control then in the reactor.
Yeah, you want to control, right? You want to avoid.
Oh, yes. Oh, yes.
Oh, that reminds me that the discussion we had, drive versus spontaneous reconnection. Daniel has introduced so-called driven versus spontaneous. It's a very difficult problem. Why? In the solar case, imagine is it magnetic free energy require a long time to build up. To build, becomes gradually over long, like days and even hours, days easily. But take a very small time to release it. Take a long time build up the crash. During the long time, it's drive time, gradually drive. But when you release it, the drive is very small because it's very short. It's more like a spontaneous. So you can say, well, maybe you need a both. You need a slow drive, fast crash. That's exactly sawtooth, right? Sawtooth is slow drive, crash. So maybe the challenge is how do you predict when exactly this crash, the trigger. What I hear today is saying like a neoclassical tearing mode can be triggered non-linearly by some large seat, right? The seat, magnitude, big seat, jump over the unstable regime. That could be one particular mechanism to jump over from stable to suddenly become unstable. In the solar case, there are competing ideas. There's a country becomes thin enough, the tearing the proximal instability becomes unstable. It becomes crashing. That's one idea. But I don't know, maybe turbulence in Adria's like a four-shock turbulence area is more like a turbulent drive. No, there's a competing idea, but they're not the same. Maybe that's a part that we can communicate between different communities. So one idea can carry over from one community to the other. No linear drive, like a neoclassical that they happen, in solar case or vice versa. Like a sawtooth crash simulation that shows that proximal instability can be triggered as part of instability onset. But it's not enough. It's still not enough. We need two full effects. So I'm saying maybe we need it all together to make sense. Yeah.
Well, I think this is a great area to collaborate because the sawtooth has been around obviously since observed for many decades, but it's still not understood really what is the trigger mechanism and why it happens when it does and what the role is. There seems to be an ideal component to the mode and then a resistive component, very fast crash, and it's not clear at all whether it's turbulence that's behind ultimately the crash or secondary instabilities or even what the Q profile is, and even whether whether you have a rational surface during the ramping phase when there's many things that are unknown, and measurements are particularly difficult in the core of the plasma. So in a tokamak, so this is certainly an area where there could be a lot of cross-fertilization, I think.
A question from EPFL, so maybe for Emanuele or Jonathan. How do you anticipate the recent advancements in gyrokinetic simulation resolution as demonstrated by Antoine Hoffman and his team from EPFL? And how this will impact the broader research landscape and in particular your current research?
So just I have a quick and general answer, not a real precise answer to the point. I don't know enough the status of this research to say that those are already a serious competition for normal standard gyrokinetic simulations. But as you have seen in all our endeavors, I think all the people sitting here, and everything which can lead to faster simulations will be welcome. If that turns out to be a game changer, we will jump on it, of course. But yes. At the moment, I cannot say anything.
And a question from the audience. Is it possible to harness these reconnections to remove the impurity particles?
I don't know whether this is something I could talk about. I know a bit about this. Generally speaking, from what I've observed certainly in tokamaks, I don't know about accelerators, but it may be the same. But the combination of it, at least for heavy impurities like tungsten, and these are present in, say, Aztecs Upgrade and JET, for example, and will be obviously there in ITER as well. This combination of magnetic islands and MHD and impurities is generally not a very good one. It seems like the tearing modes tend to suck in the impurities into the core. To be fair, sawtooth crashes can help. So this is one argument for why you might want to operate a fusion device like ITER with sawtooth. It seems like this can enable the impurities which tend to go very close to the magnetic axes. Heavy impurities are a problem in that respect. The sawtooth can actually shift them at least to the Q+1 surface, which is about a third of the way out of the plasma typically, a third of the way out of the core. So sawtooth can be beneficial, but other than that, it looks like modes like tearing modes, which are a bit further out, tend to suck the impurities in, and even modes such as edge harmonic oscillations, which are currently there during elm-free scenarios. We need to avoid elms as well, edge localized modes. These kind of modes also tend to pull in the impurities as well. So this is a very important active area of research where we need to understand the synergy between impurities and MHD. It could be that we can harness MHD, but it seems like it's often a very bad combination as well. So a very interesting area, a very good question.
Thank you, Jonathan. So it was the last question. So, and I think we have on time. So maybe first I want to thank all of you and all the audience to participate to the webinar. And I think it was a very fruitful presentation and also discussion. And so thank you. And maybe I will give the last word to Jonathan to close the webinar.
Okay, I hadn't planned that, but thank you, Magali. Yes, thank you to all the participants. We had nearly 100 today, I think, at one point. So it was, I think, I don't know, but I guess we can call that a success. And we were on time as well. And I think that the questions that were posed were excellent. I haven't done very much work for this myself. I'd like to thank the speakers who have put a lot of effort in. I know that they've collaborated with each other very carefully, and especially to Magali as well, who has put together some very good questions and done that in real time as well. So thank you, everybody. Thanks to the speakers. Thanks for IOPP, Institute of Plasma Physics, for helping us to host this. And yeah, and I hope that we'll see you again for another webinar in a few months' time. Thank you.
Thank you.
Thank you.
Thank you.
Thank you. Thank you.